Hello everyone, my name is Nicolas Dari Bako, and I'm glad to be able to present to you the work I have done regarding the determination of the Newton-Universal scattering cross-section on thorium-232 from NX and gamma measured cross-sections. First, I will tell you a little bit about the procedure to go to NN prime gamma to NN prime, then the experiment that has been done, and the result in comparison that has been made. So what is our interest here is the NN prime gamma reaction, where we have first a collision of a neutron with a target. This target will go to an excited state and will emit a gamma. We use the gamma point spectroscopy to study the inertic scattering and measure the NN prime gamma cross-sections. And therefore, we focus on the emitted gamma. We want to determine the level production cross-section of a level K, which is this contribution here. By the gamma point spectroscopy, we have information regarding the gamma de-excitation of K and the gamma de-excitation of higher energy levels to K. So, to have this contribution, the level production cross-section, we have the level K as a function of the energy of the neutron. We have to do the sum over all transitions that are emitted by K and subtract all transitions that are received by K. And here you have, therefore, the transition cross-sections. We have also a 1 plus alpha factor because we do not take into account by this method the internal conversion, and we therefore have to put the internal conversion coefficient to take into account this phenomenon. An experiment has been made at Gelina, which is at the European Commission Joint Research Center in Geel in Belgium. It is a time-of-flight facility with a neutron beam, which characteristics are written here. And the experiment took place more precisely here at the flying path 16, which is at 13 meters from the neutron beam generation, which is here. The graphene device, which is composed of a fission chamber and 4 IPHC germanium detectors, had been used. So you have a scheme here, a graphene, and here a photo. The target, which is placed here and here, is a target of thorium-232 with characteristics are here, and this analysis has been done by Elliott Party during its thesis a few years ago. The structure of the thorium-232 during this experiment has been probed up to 1647 keV, which is this level right here. 92 transitions and 52 levels have been studied. Which we have here the level scheme, and more precisely in red, you have the 70 transition cross-sections that has been extracted. These are my data that I use them to compute the level production cross-sections. To calculate the level production cross-sections, we need first the transition cross-sections of all emitted and received transitions for level K, and all the internal conversion coefficients, alpha. But from this experiment, we miss some informations, so we miss some transitions. We don't have access to the branching ratio of unmeasured transitions. We don't have access to the ICC and to multipolarities. So databases, and more precisely ENSDF, have been used in order to get this information, but because they are not fully completed, hypotheses are also to be made in order to get level production cross-sections. Hypotheses made for 23 out of the 27 cross-sections. Why do we need all this data? Because in fact, even if we don't have the two transitions measured, knowing the intensity of the both of them, we can deduce the transition cross-section of an unmeasured transition. So there are hypotheses that have been made. So hypotheses regarding uncertainties on the intensities, so 10%. ICC, when they are not known, BRIC has been used, but BRIC needs multipolarities, and an order of 2 maximum has been considered in the calculations. It enabled to compute level prediction cross-sections. So here you have a special case of this level, 56.9 kV of the thorium-232. So we want to determine its level prediction cross-section. First, the transitions that are emitted. We have one, which is here, this one in blue. Downwards, the 333.3 kV. Then the transitions that fed this level, there are three here in orange, red, and blue, and purple, which are here in dashed line because they are received and not emitted by this level. And finally, we have also a transition that has not been measured, but with this one, we can deduce, and it is in the little star here for the green transition. Do we have anything else? Maybe, but it is above the limit that we probed. Therefore, the cross-section that we compute here, and that is depicted in black, is exact up to 1.647 MeV, because above, we do not know. So it is exact here, and then we have an upper bound on the cross-section. And what I can notice is that in the thorium-232, continuum starts at low excitation energy, and quickly we are not able to measure cross-section from high energy levels. Then, regarding the total NN prime cross-section, we sum over all transitions that go downwards the ground state. Do we miss any? Probably, maybe, but if we do, they are above this limit here, and we have a lower bound on our cross-section. So here we have in black the total cross-section, and in colors all the transition cross-sections. We can see, so it is exact here, and then the circle are empty, meaning that we have a lower bound. It's not exact anymore. And we have a major contribution from the 49 kV, which is the first excited state. We also have high uncertainties, and it's because we have an internal conversion coefficient of more than 300, meaning that we have much more statistics with the electrons than with the gammas. And it's what we can see here, that our peak, the 49 kV peak from this gamma spectra, is not so much high. It's still high because we have an even nucleus, and the excitation goes mainly through the fundamental band, but we miss a lot of statistics because we don't have electrons. Therefore, because we missed a lot of statistics, we have high uncertainties on this 49 that then impacts the total NN prime cross-section. Then comparison has been made with models. So in particular here, we will focus on the difference between Thalys default and Thalys best. And we can see that Thalys default, which is in orange here, does not have a good description of the fission. We have here the evaluation in green, and also all the experimental points. And you can see the description is not good, rather than the best, which is in indigo, which has a better description of the fission. So that's why we will use mainly the best parameters then to compare our experimental points that are here. So the total NN prime gamma NN prime cross-section, elastic scattering cross-section. We can say a good agreement at higher energy with both, so our points are in blue, and we have a good agreement with both the other experimental points that are here, the models and the evaluation. But at low energy, it's not a good agreement. So we have to work on the discrimination of the signal background to improve this data. Then finally, from the NN prime gamma cross-sections and hypothesis that has been made, we managed to compute 27 level production cross-section and also the total neutron elastic scattering cross-section. But as I said before, they are missing structure information because the level scheme of the 4M32 is compact cross-section only on limit. The high uncertainties from the first historicity state come from an high internal conversion. But there is a project within the collaboration that I'm in, that I work with within, that is the purpose is to measure therefore these conversion electrons. It's called the DELCO project. There are discrepancies that have been observed, and it's a work in progress right now for the publication. So which will be at late 2023, early 2024, regarding therefore this work, and we'll have all the cross sections. Also, an improved modeling by the theoreticians. I thank you for your attention, for your time, and if you have any question, please ask them. Thank you.